So, in the previous lecture we were examining the rate of deformation tensor or the velocity gradient. Tensor. Okay, so that is what we were defining in the previous lecture, and this is the gradient of the velocity, the gradient operator acting on the velocity with no dot product in between. The gradient has one direction, the direction of variation. The velocity has the direction of motion. Okay. And therefore, you get a second order tensor in which the first index represents the direction of variation, the second index represents the direction of motion. Okay. And physically I had represented this for you. If I take two nearby locations x and del x plus delta x separated by a distance delta x, okay, the velocity at the location x is v of x, at the location x plus delta x is v of x plus delta x, and there is a difference in the velocity delta v. Okay. That difference delta v is equal to delta x dotted with grad v. Okay. That difference in velocity delta v is delta x dotted with grad v, just as in our definition of the gradient the change in concentration was delta x dotted with grad c, the change in temperature was delta x dotted with grad t. In a similar manner, the change in velocity is delta x dotted with grad v, difference here being that velocity is a vector. So, you have to take the vector difference between the velocity at two nearby locations. Okay. And physically this gives you the rate of deformation. Okay. So, for example, if the distance between two locations is delta x at the time t, and if the left and the right extreme of this line element, okay, if the left and the right extreme of this line element are moving with different velocities, that means that that line element is deforming, either stretching or rotating. Okay, if the two ends of that line element are moving with different velocities, and the difference in velocity is given by the gradient. Okay, so, the gradient of the velocity gives you the deformation locally of a line element between two locations, okay, is related to the gradient of the velocity times delta x. Okay. The difference in the velocity between two nearby locations is the gradient of the velocity dotted with delta x. So, this gradient of the velocity written in matrix form, we had separated it out into two parts. One is a symmetric part and the other is an antisymmetric part. This is general. Any matrix can be separated out into a symmetric part and an antisymmetric part, where the symmetric part is 1/2 of the matrix plus its transpose, okay, 1/2 of the matrix plus its transpose. The antisymmetric part is 1/2 of the matrix minus its transpose. Okay. Okay, 1/2 of the matrix minus its transpose. The trace of this matrix was defined as the sum of the diagonal elements of that matrix. Okay, the trace of this matrix was defined as the sum of the diagonal elements. That we saw was equal to the divergence of the velocity. Okay. So, I can define an isotropic matrix which is proportional to the identity matrix here. Okay, I can define an isotropic matrix which is proportional to the identity matrix here, whose trace is also equal to the divergence of the velocity. Okay. So, if I take the symmetric matrix and then subtract out this isotropic matrix with diagonal elements, I will end up with a matrix that is symmetric and traceless, okay, that is symmetric and whose sum of diagonals is equal to 0. Okay. And this thing is what is called the extensional strain. Okay. Okay. What are the types of deformation that each of these matrices represent? Okay. What are the types of deformation that each of these matrices represent? Okay. So, I will explain it to you in 2 dimensions. Okay. In order for ease of representation, okay, I will explain it for you in 2 dimensions for ease of representation. So, in 2 dimensions I have 2 axes, okay, x and y, okay, and the origin is the location at which I know I am trying to get the deformation relative to the origin. Okay. So, what I so if I go to some location in space, okay, so if I have some 3-dimensional flow field, okay, okay, I can go to a particular location there, okay, draw a coordinate at this location and find out the difference in velocity between this central location here, okay, this central location here and nearby location, okay, and various nearby locations. I can find out the difference in the velocity between the origin in this particular coordinate system and the nearby velocities. Okay. So, the difference is independent of the velocity at that location. Okay. It only gives you the relative velocity of nearby points relative to this point of observation, okay, the central point at which the velocity gradient is calculated. Okay. So, I will do that in 2 dimensions in an xy, okay, coordinate axis. Okay. In 2 dimensions, the divergence of the velocity is equal to half, is equal to not half, partial Vx by partial x plus partial Vy by partial y. Okay. So, I will take a general velocity gradient field. Okay. Note there is no dot product here, this is the velocity gradient in 2 dimensions. Okay. The isotropic part in 2 dimensions will just be equal to half of del dot V, okay, into 1 0 0 1, okay, plus a symmetric traceless part. Okay. Symmetric traceless, the trace is equal to 0. Okay. Where E is a scalar plus an antisymmetric part. So, this E should be, my apologies. Okay, so these are the 3, the isotropic part, the symmetric traceless part and the antisymmetric part. The antisymmetric and the isotropic part are general. The symmetric traceless part here looks to be specific because I have taken the off diagonal elements to be equal to 0. Okay. I have taken the off diagonal elements to be equal to 0. Okay. So, it looks like it is a special case, but it is actually not, because any symmetric matrix in 2 dimensions can always be transformed to this matrix by rotating the coordinates. I will not go into the details of that, it is beyond the scope of this course, but you can always convert any matrix into the symmetric matrix by rotating the coordinates. Okay. So, these are the 3 different types of deformation. Okay. So, now we know that delta V is equal to delta x dotted with grad V, okay, is equal to delta x delta y into this matrix. Okay. And now we can ask what are the types of deformation due to each of these three individual terms. Okay. So, first we consider the isotropic part. Okay. So, first we consider the isotropic part. Okay. And if we write this delta V is equal to delta x delta y into 1 0 0 1. Let me write below here. Okay. Into this isotropic part, that is half del dot V. Okay. This will give me the matrix, okay, half del dot V delta x and half del dot V delta y. Okay. So, delta V x, okay, so this is grad V will be, okay, okay. So, delta V x and delta V y is equal to this delta x dotted with grad V, okay, and this is delta x, okay, delta x delta y dotted with this gradient of the velocity, okay, and it has two components. Delta V x is equal to constant times delta x here, okay. Delta V x is a constant times delta x and delta V y is a constant times delta y, okay, the same constant, okay, half of the divergence of the velocity, okay, the same constant. Okay. That means that if I go equal distance delta x, okay, in the positive direction, then delta V x is equal to is in the positive direction and delta V y is 0. So, the relative velocity here will be in this direction, it will be in the x direction, delta V y is equal to 0. Okay. If I go the same distance in the y direction, now delta V y is equal to half delta V into delta y, whereas delta V x is equal to 0 because delta x is equal to 0. Okay. So, I will get a velocity vector in this direction. Okay. If I go in the minus delta x direction, the x velocity is reversed because delta x is reversed. Okay. So, in the minus x direction it will look something like this, and similarly in the minus y direction it is reversed. Okay. So, at any location the velocity is radially outward. Okay. Okay. And therefore, this part of the velocity field represents radial expansion or compression. Okay. This first part of the velocity field, okay, that I have shown here represents radially outward flow if del dot V is positive and radially inward flow if del dot V is negative. Okay. So, this is radial expansion or compression from a point. Okay. Recall our mass conservation equation that we had derived, okay. d rho by dt, okay, is equal plus equal to 0. Okay. And I told you that this first term, okay, 1 by rho d rho by dt is equal to minus 1 by v dv by dt, where v is the volume element of a fluid. Okay. So, this term basically represents volumetric expansion or compression depending upon whether the divergence of the velocity is positive or negative. Okay. Depending upon whether the divergence of the velocity is positive or negative, this represents radial expansion or compression. For an incompressible fluid, the divergence of the velocity is equal to 0. The density is independent of position or time. the divergence of the velocity is equal to 0. Therefore, this isotropic part is 0 for an incompressible flow. Okay. So, there can be no radial expansion or compression for an incompressible flow. Okay. So, this is the isotropic part. Okay. That is the first part over here. It represents radial expansion or compression. It is proportional to the divergence of the velocity, and for an incompressible flow this isotropic part is identically equal to 0. Okay. Let us look at the second part, okay, that is the symmetric traceless part. That is the symmetric traceless part. Okay. So, the deformation for this symmetric traceless part is grad V is equal to E 0 0 minus E, okay, or delta V is equal to delta x dotted with grad V, okay, which is equal to delta x and delta y, okay, the rho matrix times E 0 0 minus E. Okay. This is delta V x and delta V y, okay, which means that the relative velocity between nearby points is delta V x is equal to E delta x and delta V y is equal to minus E times delta y. Okay. So, that is the relative velocity between nearby points from the origin. And let us examine what kind of deformation this represents. Okay. If I go a small distance in the plus x direction, okay, delta x is equal to E delta V x is equal to E times delta x and delta V y is equal to 0. Okay. So, therefore, this is the deformation due to this is going to be in the plus x direction. The relative velocity is going to be in the plus x direction at the location on the x axis where delta x is positive and delta y is 0. At a location on the minus x axis where x is negative and y is equal to 0, right, I will get this to be minus, okay, E times delta x will be the relative velocity. Okay. So, this velocity, okay, at this point will be in the negative x direction. Okay. So, these are the relative velocities relative to the center point at locations on the x axis at plus delta x and minus delta x. Okay. For the y axis it is equal to minus E times delta y. Okay. So, the velocity at this location will be in the negative y direction. The velocity in this direction where delta y is negative will be in the plus y direction. It has the same magnitude E. Okay. So, this is the kind of deformation due to the traceless, symmetric traceless part of the rate of deformation tensor. Okay. And so, if you had an original volume that was something like this, okay, that volume is going to be stretched along the x axis and compressed along the y axis. Okay. That volume is going to be stretched along the x axis and compressed along the y axis. Okay. Okay, at a later time that volume is going to be stretched or extensional in one direction. The deformation is extensional in one direction, in this case the x direction, and it is compressional in the orthogonal direction, that is the y direction, okay, in such a way that the net change in volume is 0, okay, in such a way that the net change in volume is 0, okay, and also in such a way that the axes remain the same, they do not rotate. Okay. So, this type of deformation, okay, which is symmetric and traceless. Traceless so that there is no net change in volume. Symmetric, there is no rotation of the axis. There is extension along one axis and there is compression along the perpendicular to axis. Okay. So, this is what is called as extensional strain. Okay. This is what is called as extensional strain. Okay. So, this is in 2 dimensions. Okay. So, this is in 2 dimensions. In 2 dimensions, if you have a symmetric matrix, you know that the eigen values are real from linear algebra for a symmetric matrix. The eigen values are real and the eigen vectors are orthogonal. Okay. The eigen values are real, the eigen vectors are orthogonal, and the direction of the eigen vectors is the direction of the principal directions for extension or compression. Okay. So, for this symmetric matrix, the eigen values are real. The sum of the eigen values is equal to the trace of the matrix. The sum of the eigen values is equal to the sum of the diagonal elements of the matrix. Since the matrix is traceless, the sum of the diagonal elements is 0. Therefore, if one eigenvalue is positive, the other one has to be negative. Okay. Therefore, if there is extension along one direction, that has to be compression along the orthogonal direction. The direction of compression or extension is the direction of the eigenvectors, and for a symmetric matrix, the direction vectors are orthogonal. So, there is extension along the direction where the eigenvalue is positive and compression along the direction where the eigenvalue is negative. Both of these happen at equal rates. Okay. Extension along one direction where the eigenvalue is positive, compression along the orthogonal direction where the eigenvalue is negative. The magnitudes are the same in both cases. Okay, for the extension and compression, in such a way that there is no change in volume. Okay. The rates of extension and compression, the magnitudes of the rates of compression and extension are equal, such that the sum of the diagonal elements is equal to 0. Okay. So, there is no net extension or compression, and also the eigenvalues are orthogonal to each other, and in this deformation, since there is extension along one direction and compression along the other direction, the direction of extension or compression is the same as the direction of separation. Okay. Okay. The direction of extension or compression is the same as the direction of separation. So, there is no deformation perpendicular to the direction of separation, therefore, there is no rotation, okay, because there is no deformation perpendicular to the direction of separation, and therefore, there is no rotation. This can be extended to 3 dimensions. Okay. I told you that in 3 dimensions, the rate of deformation tensor, the extensional part of the rate of deformation tensor, is equal to the symmetric part minus 1/3 of the divergence of the velocity times the identity tensor. This matrix is symmetric and traceless. Okay. Eigenvalues lambda 1 are real, okay, and eigenvectors E1, E2 and E3 orthogonal. These are the properties of a symmetric matrix, and the matrix is also traceless, okay, which implies that the sum of the diagonal elements has to be equal to the sum of the eigenvalues. The sum of the diagonal elements is 0, therefore, lambda 1 plus lambda 2 plus lambda 3 equals to 0. Okay, the sum of the eigenvectors has to be equal to 0. Okay. So, there are two possibilities here. All three eigenvalues cannot have the same sign because the sum has to be 0. Okay. So, you could have eigenvalues out of which 2 are positive and 1 is negative, 1 is positive and 2 are negative, or 1 is positive, 1 is negative and 1 is 0. Okay. So, those are the three possibilities. And in 3 dimensions these represent different kinds of deformations. Okay. Okay. Okay, so I am drawing a 3-dimensional space here, x, y and z. X is perpendicular to y and z, okay, it is perpendicular to the plane. Okay. You could have 3 different types of deformation. One is if, okay, lambda x greater than 0, lambda y greater than 0, lambda z less than 0. Okay. These x, y and z that I have plotted here are the principal directions, okay, that are along these coordinate directions, okay, because these eigenvectors are orthogonal. Okay. So, basically at a given point I find out the symmetric traceless part of the rate of deformation tensor, determine its eigenvectors and align my coordinates with its eigenvectors. Okay. If lambda x and lambda y are positive, then there is extension along the x and y directions and compression along the z direction. Okay. Okay, so, we will have extension along the x and y direction and compression along the z direction. Okay. Okay. Extension along the x direction and compression along the z direction. There is extension along 2 axes and compression along 1 axis. So, it is called biaxial extension. Okay. That is one mode of deformation. The second mode of deformation is where 2 of the eigenvalues are negative and 1 of the eigenvalues is positive. So, for example, if you have lambda x less than 0, lambda y less than 0 and lambda z greater than 0. Okay. So, there is compression along the x and y directions and extension along the z direction. Okay. So, so this extension, there is compression along the x and y direction, so and extension along the z direction. Okay. Okay, so, this stretching along the z direction and compression in the xy plane. Okay. This is called uniaxial extension. Okay. Okay. So, these are 2 different kinds of deformation, and the third one is what is called planar extension. There is extension along one direction, compression along the perpendicular direction and no deformation along the third direction. That is, if you have lambda x is greater than 0, lambda y is less than 0 and lambda z is equal to 0. There is no extension or compression along the z direction. Okay. There is no extension or compression along the z direction. There is extension along the x direction and compression along the y direction, and that is the field that we had examined over here. Okay, there is no variation in the perpendicular z direction. Okay. So, in 3 dimensions these are the 3 kinds of deformation that can take place due to the symmetric traceless part of the rate of deformation tensor, which is extensional strain, which has 0 trace and is symmetric, and it represents deformation where there is extension along 1 or 2 directions, compression along the remaining directions, and no deformation where the eigenvalues are 0. Okay, so this is the second type of deformation that can take deformation due to the symmetric traceless part of the rate of deformation tensor. So far I have discussed the isotropic part, radial compression or extension proportional to the divergence of the velocity, which results in volumetric expansion or compression, and which has to be 0 when for an incompressible flow where the divergence of the velocity is 0. The type of deformation due to the symmetric traceless part, which could be either uniaxial, biaxial or planar extension, in which there is extension along 1 or 2 axes and compression along the other one, perpendicular axes because this is a symmetric tensor whose eigenvectors are perpendicular. There is no change in volume due to this deformation because the trace of this symmetric traceless tensor is 0, and there is also no rotation. The third one is due to the antisymmetric part of the rate of deformation tensor, which I will continue in the next lecture. I will see you then.